Hi folks, this is our first video on stereochemistry. I'm going to be talking about the concept of stereoisomerism, as well as the Cahn-Ingold-Prelog system of assigning configuration to chiral centers. Before we delve in, I want to give you an overview of isomerism. You've seen the term isomer before in the realm of constitutional isomers. But isomers more generally just means compounds that are made from the same parts. For organic chemistry, that's going to mean you have compounds made from the same atoms, meaning they have the same molecular formula, and yet those compounds are still different from each other. For today, we're going to consider two different classes of isomers: constitutional isomers and a new type called stereoisomers. Constitutional isomers will have the same molecular formula, but a different connection of atoms. You could also call this a different constitution. Stereoisomers will have the same molecular formula and the same connection of atoms, and yet the way the atoms are arranged in space will differ. To start our discussion of stereoisomerism, I'm going to show you some comparisons of objects and their mirror images, and these first comparisons are not going to be organic chemicals. Let's consider a pair of sunglasses with pink lenses as our object A. Imagine holding this object up to a mirror, and then on the other side of this mirror, I'm going to draw the mirror image of A. I'll call this mirror image A'. If you picked up A' and rotated it, you could completely place it on top of A, and it would look the same as the original A. If this is the case, we would say our object A and its mirror image A' are superimposable. By superimposable, I mean that A' could be rotated to perfectly overlay our original A. We would say, in this case, that A and A' are identical. And if an object and its mirror image are identical, then they are achiral objects. So we would say our original object A, as well as its mirror image A', they are both the same achiral object, where achiral means non-chiral. Now let's consider a pair of sunglasses where only the left side has a pink lens. Imagine holding this object B up to a mirror, and then I'm going to draw the mirror image of B on the other side of this mirror. I'll call this mirror image B'. Notice that our original pair of sunglasses B is missing the pink right lens, whereas the mirror image B' is missing its left lens instead. In this case, our original object B and its mirror image are non-superimposable. There is no way that I can rotate around my mirror image B' to make it perfectly overlay with my original B. In this case, B and B' are non-identical, and we would say that both B and B' are chiral. Now we'll consider the concept of chirality as it relates to molecules. We'll use the term chiral to describe molecules that are non-superimposable on their mirror images. And we'll use the term achiral to describe molecules that are superimposable on their mirror images. In organic compounds, the most common source of chirality is having a carbon with 4 different substituents on it. We would call this carbon a chiral center or a chiral carbon. Let's imagine a molecule A. I have a central carbon attached to an alcohol group, a hydrogen, a CH3 group, and a chlorine. We would say that this central carbon is attached to 4 different substituents. Let's imagine holding molecule A up to a mirror and drawing its mirror image. This is our mirror image A'. Let's imagine rotating A' around 180 degrees to see if it's going to look exactly like the original molecule A. If I keep the OH group in the same position and then rotate around the rest of the molecule, I get a line to hydrogen on the right. My chlorine, that was a dashed bond pointing toward the right, becomes a wedged bond pointing toward the left. And my wedged methyl becomes a dashed methyl on the other side. This other representation of A' is the same molecule as our original A', just rotated. Let's compare this rotated image of A' to our original molecule A. These are not the same compound. Notice that the positions of the chlorine and the methyl group are changed between the two. We would say that A contains a chiral center, and therefore molecule A is chiral. A' is the non-superimposable mirror image of A, and A' also contains a chiral center, and is therefore chiral as well. We would describe the relationship between chiral molecule A and its non-superimposable mirror image A' to be that those compounds are enantiomers of each other. I want to talk about spotting chiral centers within organic molecules. Most broadly, you're going to be on the lookout for carbons with 4 different groups attached to them, known as 4 different substituents. Let's consider this alkyl halide A. The carbon that I'm pointing to is a chiral center. This carbon has a methyl group attached, an ethyl group attached, a chlorine, and a hydrogen. So even though 2 of the groups are carbons, the methyl and the ethyl, they're different substituents because they contain different numbers of carbons. Let's imagine holding up molecule A to a mirror. This is our mirror image, A'. We could rotate this molecule around 180 degrees to see if it looks like the original molecule A. When I flip A' around, the wedged chlorine becomes a dashed chlorine. Both of these representations are the same molecule A', I've just flipped it over horizontally. The mirror image of A' also contains a chiral center. And this is not the same molecule as our original A. Notice that in molecule A, I have a wedge chlorine, and in my rightmost representation of A', I have a dashed chlorine. These 2 molecules are non-superimposable. Because A and A' are non-superimposable and they're mirror images of each other, we would describe them as enantiomers of each other. Now let's consider this 6-membered ring containing a bromine and an alkene. The carbon that I'm pointing to is a chiral center. It has a bromine attached, a hydrogen attached, and 2 different types of carbons attached to it. This carbon is an sp3 hybridized carbon, and this carbon is sp2 hybridized. These differently hybridized carbons count as different substituents. Let's hold up molecule B to a mirror. This is the mirror image of B, known as B'. I'm going to rotate around B prime, flipping it 180 degrees horizontally to make it look as similar to the original B as possible. When I flip this molecule over, my dashed bromine on the left becomes a wedged bromine on the right. Similar to my original molecule, B prime also contains a chiral center. Now we want to look at our two different representations, B and B prime, and see if they're superimposable. They are not. While B has a dashed bromine pointed up and to the right, B prime has a wedged bromine at the same position. Because these molecules are non-superimposable and they're mirror images of each other, they are enantiomers of each other. Notice that between A and A prime, and then B and B prime, the only thing that I've changed in my drawings from my original molecule to the representation on the furthest right is that I changed dashes to wedges, or wedges to dashes. This is actually a general way to quickly draw a molecule's enantiomer. You would redraw most of the molecule in the same representation as before, and then all you would need to do is switch any wedges to dashes and dashes to wedges. This would give you the molecule's enantiomer. Organic chemists have a system of assigning stereochemistry to convey information about the chirality of a center within a molecule. We call this assigning configuration. This is also known as the Cahn-Ingold-Prelog system, and this is essentially nomenclature for stereochemistry and chiral centers. The first step to assigning configuration is to assign priorities to each group around your chiral carbon. Atoms with higher atomic number will have higher priorities. Here is an example molecule featuring a chlorine as well as an ether group. This carbon I'm pointing to is a chiral center. It has 4 different substituents attached to it. I'm going to look at everything attached to that chiral carbon and assign its priority, 1 through 4. Chlorine has the highest atomic number of these groups, so it is priority 1. Oxygen has the next highest atomic number, so it's number 2. Carbon has the 3rd highest atomic number, meaning it's group number 3. And hydrogen has the lowest atomic number of the whole periodic table, so it's going to be number 4. Sometimes when you're attempting to assign priorities, you'll run into a tie. This could come up if you run into 2 of the same atom, for example, 2 different carbons or 2 different oxygens. If there's a tie, you want to make a list of all of the atoms that are attached to the tied atoms. You'll order these lists in order of decreasing priority. You want to look out for a tiebreaker based on atomic number. Let's look at the following molecule. I have a 4-carbon chain with a wedged chlorine at position 2. I've identified my chiral center, which contains 4 different substituents. One of these, a hydrogen, is not yet drawn in, so I'm going to draw that in with its appropriate type of bond at this point. Because the chiral carbon already has 2 line bonds as well as a wedge, the hydrogen has to be a dash. Now I'm going to try to assign priorities to everything attached to the chiral center. Chlorine has the highest atomic number, making it priority 1. And hydrogen has the lowest atomic number, giving it number 4. Now my other 2 groups are currently tied. I'm comparing carbon to carbon. I'm going to make a list of all of the bonds that those two different carbons have. My methyl carbon has a bond to the carbon of the chiral center and 3 hydrogens. The carbon of the ethyl group has a bond to the carbon of the chiral center, the carbon of the methyl group attached to the CH2, and then 2 hydrogens that aren't drawn. I have a tie comparing carbon to carbon, but I have a tiebreaker at the second item in the list. I'm comparing a hydrogen to a carbon. Carbon has the higher atomic number, so my tiebreaker gives the ethyl group the higher priority. The CH2 of the ethyl group is priority 2, and the methyl group is priority 3. Now let's consider the following molecule. The carbon attached to bromine is a chiral center. It has 1 hydrogen that's not drawn that I need to draw in at this time. This hydrogen is wedged. Bromine is priority 1 because it has the highest atomic number. And hydrogen is again priority number 4. Now I need to compare this carbon of the ring to this carbon of the ring to figure out the priorities of those different groups. The CH2 carbon is attached to the original chiral center, another carbon, and 2 hydrogens. This carbon of the alkene is attached to the original carbon. It has a single bond to another carbon, This carbon of the alkene is attached to the original chiral center, and then it has 2 bonds to another carbon. You list these separately in your list making. Then that carbon has another hydrogen that's not shown attached to it. In each case, my list starts with 2 carbons, but there's a tiebreaker at position 3. In my list, I'm comparing carbon in one list to hydrogen in the other. This makes the alkene carbon priority 2 and the CH2 carbon priority 3. As a third example, let's investigate this molecule that contains 2 alcohols. I've identified my chiral center. The OH group has highest priority, and the hydrogen has lowest priority. Then I'm comparing carbon to carbon, and I need to make a list of everything attached to each carbon. This carbon of the CH2 group is attached to an oxygen, another carbon of the chiral center, and 2 hydrogens. The other carbon, the central one of a tert-butyl group, is attached to 4 different carbons. I have a tiebreaker at the first position in my list this time. I compared oxygen to carbon, and oxygen has higher atomic number. The carbon with the oxygen attached to it is priority 2, and the carbon with 4 other carbons attached to it is priority 3. After assigning priorities, the next step is to sketch a Newman projection, looking down the bond where your chiral carbon is the front carbon of your Newman projection, and the lowest priority group is directly behind it. Then you're going to want to trace around from number 1 to number 2 to number 3. If these go in a clockwise order from 1 to 2 to 3, your chiral carbon has R configuration. If you trace from 1 to 2 to 3 counterclockwise, your chiral center has S configuration instead. Let's evaluate that same 2-alcohol containing molecule from before. Here I've listed the priorities of the 4 different substituents. We're going to want to imagine looking down our molecule from the front chiral center to the lowest priority group, in this case a hydrogen. In this case, my hydrogen is already drawn as dashed, so I'm pretty close to my Newman projection already. If I look at my molecule opposite the direction of the hydrogen for my Newman projection, I get something that looks like this. This is my front carbon, the chiral center, and the hydrogen is directly behind it. I would think about starting at position 1 and tracing around from 2 to 3. Going from 1 to 2 to 3 takes me around counterclockwise, so my original chiral center has S configuration. Now let's look at this molecule containing a chlorine and an ether group. I've numbered the priorities of my different substituents around my chiral carbon. Because the hydrogen is wedged instead of dashed in this molecule, this is a trickier situation for imagining your Newman projection. You need to imagine looking at this molecule from below the page, opposite the hydrogen coming out at you. When you look at this molecule, imagining you're below it and looking up at it, the groups 2 and 3 will be on opposite sides. From your vantage point in the Newman projection, you could still draw the chlorine pointed up, but then now the oxygen group and the ethyl group have switched sides. In this Newman projection, your chiral center is the front carbon and the hydrogen is directly behind it. I'm going to trace around my curve from 1 to 2 to 3. Notice in this case as well, I've gone around counterclockwise, so this chiral center as well has S configuration. Assigning configurations as R or S can be helpful in figuring out the relationship between 2 compounds. Here I have 2 different drawings of molecules. Here I want to figure out, are they the same molecule or are they stereoisomers with different spatial arrangements of their atoms? I'll start by looking at the molecule on the left. I've numbered my priorities with chlorine 1, oxygen 2, carbon 3, and hydrogen 4. Because hydrogen is already a dash, this is my easier Newman projection scenario. The positions 1, 2, and 3 are essentially where they need to be already. I'll trace around from 1 to 2 to 3. I traced around 1 to 2 to 3 clockwise, meaning the chiral center has R configuration. I could write R near that chiral center. Now let's do the same thing for the molecule drawn on the right. This is our more difficult Newman projection scenario because the hydrogen is pointing up at you. So to look down the bond from the chiral center to the low priority hydrogen, you need to imagine viewing this molecule from below and looking up at it. When you view the molecule from below, 2 of your numbers will switch sides. Notice I left 1 facing in the same direction that it was originally, and then my number 2 and number 3 have flipped sides. I could trace around from 1 to 2 to 3. This goes counterclockwise, so I have configuration S. I could write S near my chiral center. So my 2 different compounds have different configurations. One is R and the other one is S. If they have different configurations, they cannot be the same molecule. Instead, these molecules are enantiomers. They are each chiral, and they are non-superimposable mirror images of each other. My system here for determining if my molecules are the same or enantiomers of each other, I had 2 steps. First, I assigned all chiral centers as R or S. If these chiral centers are inverted, meaning one is R and one is S, these molecules are enantiomers of each other. If we determined that the chiral centers remained the same, either both were R or both were S, these would instead be different drawings of the same compound. I want to end by talking about naming in cases where you have chiral centers. This is similar to the nomenclature we saw before. The only difference is that you indicate your R or S configuration at the beginning of the name in parentheses, followed by a dash. Let's consider the following molecule. I have a parent chain of 5 carbons, and off of that parent chain are 2 methyl groups. So far, the name of my compound is 2,3-dimethylpentane. Notice that position 3 is a chiral center, so we're going to assign priorities to the different groups attached to it to determine if this is R or S. To have more space to work, I've redrawn my molecule. I next need to explicitly draw out my hydrogen. In this case, it is dashed. Here, I've numbered the priorities of the 4 substituents around the chiral center. And if you go through the Newman projection and tracing around from 1 to 2 to 3, you get configuration R. The full name of this compound would be R2,3-dimethylpentane. In summary, today's video introduced the concept of stereoisomerism, or the fact that even if you have molecules with the same connection of atoms, you can have different spatial arrangements of those atoms. I talked about molecular chirality and the concept of enantiomers, and I finished by talking about assigning configurations as either R or S. That's it for this video. I will see you in class.